Okay, I think most people have joined, so happy afternoon, happy Tuesday afternoon, everyone. Welcome to another Paleoberg seminar. And I'm very happy to announce that this week's speaker is Alice Paine from the University of Oxford in the UK. And she will be talking about exploring the Quaternary mercury cycle. So for the people that don't know it, I will quickly explain the format of today's seminar. So first we'll start with a quick welcome and announcements. I'm doing that right now. Then we'll have the talk, which is around 30 minutes, followed by a moderated Q&A that will be around 10 minutes. And please don't forget to send your questions via the chat to the questions at Paleoberg's host, who will answer all your questions. I would like to stress that today we don't have a tea time talk. But if you have any further questions for Alice, she has told us that she's very happy to answer you via email or her socials, which will be linked in the chat shortly. So a bit more housekeeping. Paleobergs values the participation of all folks interested in the paleosciences. And please remember to abide by our code of conduct during today's seminar. You should have signed this prior to signing up for Paleobergs. If you somehow haven't read this, then please go to our website and still read through it if you would like to. So you can ask questions by chatting to the questions at the Paleobergs host. If you would like to ask a question yourself, you can also use the raise hand function and we will ask you to ask a question. Also, if you have any technical issues, you can ask them to the questions at Paleoberg's host. So one more thing, we also have closed captions built into Zoom, and you can use the CC button to either show them or hide them, whatever you prefer. And finally, we're always happy to hear about other outstanding early career scientists. So we'd be very happy if you can nominate another one. That can be done in the link here. This will also be dropped in the chat. And we're also very happy to hear about any feedback that you have for us, either demographic, like who is watching the seminars, or if you have any criticism or tips for us, we would also love to hear that. And this link will also be dropped in the chat window. So now that's out of the way, I would like to tell you a bit more about today's speaker, Alice Paine. So Alice did her bachelor's in physical geography at the University of Leeds in the UK. She then moved on to do her master's at the University of Durham. Currently, she is in the very final stages of her PhD at the University of Oxford. And then in September, she's moving on to a postdoc at the University of Basel to work on the MITRA project. So without further ado, I would like to hand the screen share over to Alice, and you can start with your presentation. Thank you, Alice.
Thank you so much for that introduction. Thank you also for the invitation to come speak today. It's I make no I'll openly say that Paleoperks has been an organisation that I've had great respect for a long time, and so to actually be here giving a talk is really cool, and a nice way to close out the PhD as well, to talk about what I've been essentially selling my life to for the past 4 years. I wanted to start with this slide and this quote because change really is the theme that is woven throughout this talk that I'm going to give today, and the research that ultimately this talk is about. It's a story of change. It's a story of how the Earth system has evolved over the past million years or so, and what we can do to understand different parts of how this change has happened, because we know change doesn't happen in isolation. Change is not a single entity. It can manifest in different ways. And the ways that sort of the modes of change we're going to be focusing on in particular is how the mercury cycles changed. And so this is the title of the talk and also of my thesis that I'm submitting next week. So as Nina said, very much in the closing stages. And this talk will really be a summary of what I've been doing for the past 4 years. So we're going to sort of talk through the different records I've been looking at to explore this cycle, the cycle of mercury, which is the element, and look at how the sort of key themes and key lessons that we can take from this, with change being the theme of understanding ultimately how this cycle has changed throughout the past million years or so, and how we can disentangle these changes using lake sediment records in particular. And you'll see I've included a gorgeous photo of a lake here. This is Lake Prespus. This is one of the 3 lakes that I'll be referring to today. And you can already see, you know, the landscape is peppered with snow. There's mountains. There's undulating topography, and all these things will, as you'll see, will become significant to and pertinent to the discussion as we move through the talk. So before I start, I just want to clarify on the terminology I'm using, because I appreciate there's in paleoclimate, there's lots of different terms, and I'm sure a lot of you are familiar with them already, but just in case anyone isn't, I thought it'd be good to kind of touch base and make sure everyone is clear. So the Quaternary, as I refer to it here, refers to the past 2.5 million years of Earth's history. It's divided into two epochs. So we've got the Pleistocene, which is about 2.5 million years ago to roughly 11.7 thousand years ago. At which point then the Holocene starts, which is of course the epoch that we are in today, subject to debate whether we are still in the Holocene or whether we've moved to Anthropocene. But that's someone else's area of expertise. So I'm going to skirt around that, and we're not going to be too concerned about that. So as it relates to today, we're going to talk about the Pleistocene and the Holocene, and those will be the two epochs that we're referring to specifically. And so what was changing on the Earth during the Quaternary, the past 2 million years? Well, as you can see, a lot was changing on Earth. This is an artist's impression of what the Earth may have looked like during the last glacial maximum, so roughly about 26,000 years ago. But it can be taken as a sort of rough analogue for glaciations, because we know the Earth was repeatedly glaciated throughout the Quaternary, and so you had the advance of high latitude ice sheets that also grew in volume during this time. And this happened in a very cyclic nature. So you had the waxing and waning of ice sheets corresponding to the glacials, so high ice volume, interglacials, low ice volume. And with these oscillations, you had changes in dust export. So you had very high atmospheric dust concentrations during glacials, thinning of vegetation and recession of ecosystems during glacials, lowering sea levels, and continental glaciers also becoming a lot larger and advancing. And subsequently, the opposite happened during interglacials. So you had very lush vegetation and ecosystems, reductions in dust, reductions in ice sheet volume and extent, and rising sea levels. So you've got this very distinct oscillations between the two different states of the Earth system, if you like. And you may be thinking, well, that's all well and good, but why are these changes important to mercury, the element? You know, that's what the talk today is about. Why are these changes actually important, and why do we care? We care because the biogeochemical cycles of the Earth are intrinsically coupled to these climate states. As I mentioned at the start, changes don't happen in isolation. Changes happen as part of interwoven, interconnected feedbacks and loops and systems. And the climate system is certainly one of those, or at least exhibits that kind of behavior. And so changes in the climate system and changes in the surface environment of the Earth also elicit change in the biogeochemical cycles too. And when I'm talking about biogeochemical cycles, I'm talking about the movement of different elements between the atmosphere, the solid Earth, and then the biosphere, or the terrestrial Earth, if you like. So that's like forests, oceans. These obviously can, of course, be distinguished further into different spheres. But as keep things nice and simple, we'll just think atmosphere, surface, environment, and then solid Earth. So sort of subterranean regions. And so given that the biogeochemical cycles are coupled to the climate system, mercury is particularly a particularly interesting element to look at when we're thinking about how climate is affecting biogeochemical cycling, because it's an extremely rare element, but also it's an extremely toxic element when it's in the surface environment, because it can interact with different components and different substances in this realm, which makes it very toxic to living creatures, and it can bioaccumulate very readily too. And so it can really the concentrations can really mount up in different what we call sinks on the Earth's surface. And that's not good news. We don't want that. And so understanding how this element moves and what causes this element to move in between different compartments of the Earth system and different sinks is really, really important for us to know. And then the problem is, of course, we are only limited in how much we can actually, how far into the past we can look directly, because human beings have not been here for very long, and we've got a very limited window of direct observation. However, it's crucial that we understand how mercury oscillates during the glacial and interglacial cycles too, because these are ultimately analogues for the kind of climate changes that we may expect to see in the future. So very, very abrupt changes that affect all compartments of the Earth system. And so given that we can't directly observe these, given the timescales they occur on, we need to look further into the past and see how Mercury has changed in the past. And on this slide, I included some of the key uncertainties that we have in relation to this cycle on these kinds of timescales. So for example, we don't know fully exactly how sedimentary records, or at least terrestrial records, accumulate and retain mercury on these timescales. And so I should probably state as well, sedimentary archives are going to be what I'm mainly focusing on in this talk. There are ice core records of mercury, and these are being developed continuously and sort of growing in number. However, sedimentary records we're going to focus on for now. And exactly how these archives retain mercury and accumulate mercury, the processes, the mechanisms are still very much, there's lots of gaps in our understanding. And so we need to, that's a really key area for our focus. If the processes that may drive cycling of mercury between the environmental compartments actually changes between environments, so between, for example, polar, tropical, mid-latitude sites, are these any different? Do the processes change, or are there some kind of consistent processes that are sort of universal wherever you go on Earth? Ultimately, how the mercury cycle has evolved on these timescales, there's not many studies that have looked at this in real depth. Especially in this Quaternary time domain. We've got lots of modern studies. We've got an increasing number of studies in deep time, so talking like Cretaceous, Jurassic periods of time. But in this Quaternary period, there's not as many. And so there's a lot for us to learn in this area. And ultimately, the last point is the key why behind what us doing this. We need to know how sensitive the global mercury cycle is to climate change on different scales. Because with that knowledge, we can then think about the future and think about how sensitive the mercury cycle might be to change as we continue to morph and change our Earth's climate and at unprecedented rates. So it's really important we understand how that could affect mercury and what impacts that could have on ecosystems and society. And so, as alluded to at the start, change being the key theme, we need to define the different scales of change that I'm going to be talking about today. And as I alluded to just then, you've got local scale changes happening on annual scales, and these are within direct observation, so we can measure these directly. However, in this piece of research and in this talk, we're looking mainly at the regional and global scales of change. And these are the changes that happen maybe over hundreds, thousands of years that exceed direct observation. And so this is where we need to put our forensic glasses on. This is where we need to put our sort of time travel glasses on and start to look back in time and figure out how we can look back in time and use the geological and sedimentary record to look at mercury further back in time. And so number 2 is highlighted because that's where we're going to start with the first chapter of this story. And with this first chapter, we're going to focus in on the last glacial period, so the last sort of 100,000 years of Earth history, and a history of mercury cycling. And to do that, we're going to look at the lakes of Lake Ohrid and Lake Prespa. These are 2 lakes located in the Balkans, actually slap bang next to each other, as you can see via the photo on the left there. They're both tectonic lakes, so they were both formed by tectonic activity in the Balkan region. And both of the core sections that we analysed here correspond to the most recent 100,000 years of Earth history. And so the key question that we wanted to explore by looking at these 2 lakes in tandem is, do they record similar changes in mercury cycling? And so our hypothesis was these lakes are slap bang next to each other. They're both tectonic lakes. They're both in the same kind of environment. We would expect the mercury records to be similar or fairly similar in terms of the signals they retain. But as is the case in science, that wasn't the case. And our hypothesis was proved to be not correct. So as you can see here by the 2 mercury profiles that I've pasted here, Lake Ohrid at the top and Lake Prespa at the bottom, the spikes that we see in mercury are occurring at different times. So the maxima in mercury are happening at different times. And the plots essentially look very, very different. If you saw these 2 plots, you would not think that they were 2 lakes located next to each other in exactly the same place. And bear in mind as well, these 2 lakes will have experienced exactly the same climate changes So during the last glacial cycle, we had, the progressive growth of the ice sheets. We had the corresponding change in temperature, ice extent, all these kinds of things. These two lakes would have experienced exactly the same thing. And so the fact that their mercury records are so different actually suggests to us that it's not just global scale climate changes that are affecting the mercury composition of these lake sediments. There's something else that must be going on. And so thinking about the first difference between the two, aside from the visual fact that they look very different, one of the key differences between these two lakes is the fact that mercury appears to be hosted by different compounds. And so just for a bit of background, following deposition into a lake, mercury can be buried into the sediment in relation to the availability of what we call a host phase. And this host phase effectively acts like a shuttle. So mercury will attach to this host phase and then be pulled down and sequestered into the sediment by this phase. And this may be organic carbon, this may be detrital or clastic minerals, so like silicic particles that you get from the catchment that come in, are washed in by rivers, rainfall, that sort of thing. It's important to note here that only a small amount of the variations in mercury, so the changes in mercury, only a small amount of this can be explained by the availability of these host phases. So what that essentially means is that mercury is doing its own thing a lot of the time. Like the signals we see are not reliant just on more organic carbon or more detrital materials being pulled down into sediment. Mercury is doing its own thing, but there is a slight bit of covariance there. And the small bits of covariance we do see, they are different between the two lakes. And so Lake Prespa, you see a positive, albeit weak, correlation with organic matter. Lake Ohrid, you see a positive correlation with detrital minerals instead. So you've already got this key difference between the two lakes, that some certain aspects of the mercury signals are being pulled down by host phases, not all of it, only a small amount is, but the mercury that is being sequestered by these host phases are different between the two lakes. So already key difference there, but including the bubble on the right hand side there, a key sort of take home message is, given how weak these correlations are, changes in mercury supply to the lake appears to be the most dominant control on the signals. So it's not just the availability of organic carbon and detrital minerals. Like I said, mercury is very much doing its own thing. And it's the amount of mercury actually present in the lakes that we suspect is causing the signals to appear the way they do. And so that leads me on to the second difference, which is how the different mercury records respond to glaciation. And so in Lake Ohrid, we see the signal in mercury peak between sort of 35 and 12,000 years ago. So that's corresponding roughly to the height of glaciation. So sort of peak, soil erosion, detrital mineral influx due to glacial action, due to wind-driven erosion, recession of vegetation, all these glacial processes making a very harsh, very abrasive environment where you've got a lot of sediment coming into the lake, and we think mercury too. Whereas Lake Prespa, the largest signal, and you'll see that is a really prominent signal here, and it really stands out amongst the signals prior to it. We think that's actually to do with deglaciation. So after the peak glacial conditions experienced in the catchment, you had this massive influx of mercury related to the melting of glaciers. Potentially, if parts of Lake Prespa were frozen over, if mercury accumulated above the ice, once the ice had melted, it would mean, again, a lot more mercury going into the lake. The abrupt thawing of permafrost in the catchment too. So all these things driving a huge and overwhelming amount of mercury into this lake during deglaciation instead. And the third difference with these two lakes is the Holocene signals too. And so it's kind of pretty self-explanatory, this slide. So Lake Ohrid, you see decreasing mercury as you move through the Holocene. Lake Prespa, instead, you see a sort of net increase in mercury. And actually, a lot of the increase in mercury occurs in conjunction with increase in bioproductivity too, suggesting that maybe that has something to do with the mercury signals, potentially due to the action of algae and these other sort of autotrophic organisms in the water column, helping to further pull mercury out the water column and sequester it down sediments too. And so again, different processes, whereas in Lake Ohrid, during that same period of bioproductivity in Lake Prespa, we see nothing really happening. In fact, the decrease in mercury. So further attesting to the differences between these two lakes. And so that kind of leads us to the concluding question we had, was why do the two lakes, despite being so close together, why have they recorded such different signals? And we suspect it's to do with the differences in the basin size and bathymetry. In a nutshell, Lake Prespa is incredibly shallow, especially relative to its surface area, which is actually fairly comparable to Ohrid, whereas Ohrid is incredibly deep, and it's an incredibly deep system. And what you have there essentially is differences in the sensitivity of these lakes to the influx of different elements. And so, for example, if you were to deposit a given quantity of mercury into Lake Prespa, the lower volume means that would be substantially more poignant and profound than the same given quantity of mercury deposited in a more voluminous lake like Ohrid. And the differences in bathymetry also mean that these lakes have different sensitivity to climate changes too. And so if you had an influx of mercury coming from melting permafrost and glaciers accessing Lake Ohrid, the higher volume would mean it would have much less of an effect than if it went into Lake Prespa, which is incredibly shallow and is therefore a lot more sensitive to changes in sedimentation and climate and evaporation and precipitation and all these different factors. And so ultimately, the conclusion of this part of our work was that it's really lake-specific features that appear on these timescales, especially to dictate how mercury is preserved in the sedimentary record and the kinds of processes that these signals capture. And so there is a paper associated with this work. There's a QR code on the screen there, but also you'll be able to find on my ResearchGate and on my website as well links to the paper where you can have a read more about these records and what they can tell us about mercury. So chapter 2 of this journey, we're looking at Lake Besuntui. So going slightly further south to warmer climates, more tropical climates. Lake Besuntui is a crater lake. It formed roughly 1 million years ago following a meteorite impact. And as a result, this is a lake that, unlike Prespa and Ohrid, where you had rivers flowing into it and you had groundwaters, all these kinds of things, Lake Besuntui is completely isolated from the regional hydrological network because it is it's essentially just a hole in the ground where the meteorite hit. And it's the only natural lake in Ghana. And so it's almost like a perfect little petri dish for environmental change. It just anything can go in, but it has no way of getting out other than water by evaporation. And so what we can do is we can use the sensitivity of this lake to hydroclimate because given this closed nature, the water level and the lake itself is very sensitive to changes in precipitation and evaporation, so hydroclimate. And we can ask, well, has hydroclimate affected mercury? And we can really test whether hydroclimate is a driving factor in mercury cycling in this lake. And similar to Prespa and Ohrid 2, this sequence corresponds roughly to the past 100,000 years or so. And from what we found with the mercury data is there's two potential drivers of variability in mercury in Lake Besuntui on these kind of timescales. Number one, changes in mercury supply, and number two, the availability of organic matter. So this host phase that I was talking about before. First change in mercury supply. So similar to Prespa and Ohrid, mercury supply appears to be really important in terms of the mercury signals that this lake preserves. And what we find is that that higher mercury concentrations actually correspond to higher lake levels. And on a broader scale, if we zoom out a little bit, this also corresponds to wetter conditions across North Africa and the Mediterranean. So it looks like, or at least the question we can ask is, does more rainfall act as a way to increase the mercury supply? Is there mercury being rained out of the atmosphere into Lake Besuntui, and so therefore when you have more rainfall, would you expect there to be more mercury in the lake? And given the fact that the lake level of Lake Besuntui is sensitive to hydroclimate, in that you have higher lake levels during wetter periods, and particularly during, for example, the Holocene, where you had certain periods where the lake actually overflowed the top of the rim because it was so wet. And so our hypothesis, or at least our theory, is that rainfall is constituting the main source or driver of changes in mercury supply to this lake. But then you also have that effect in conjunction with the availability of organic matter. because a deeper lake means a lake that's more productive, but it also means more a more stratified or layered water column, which essentially causes the bottom waters and sediments to be incredibly oxygen depleted, which is really, really good for burial of organic carbon. And actually, we find that there is a positive correlation between mercury and organic carbon in the system, albeit not the strongest correlation. Of course, like Lake Presburn and Ohrid, it's still fairly weak. But what we do find actually is, given that this correlation does exist and it is positive, it seems that or it could be at least suggested that the effect of organic matter availability is having some effect on mercury too, and therefore during wetter periods you've got more organic matter being buried and more organic matter shuttling mercury into the sediments as a broad mechanism. And there's like a coupled effect between more rainfall causing more mercury to actually enter the lake, and then more organic matter driving that transmission from the water column into the sediments. And so this is just a schematic diagram that essentially summarizes what we just talked about then. So the key points being that mercury fluxes appear to increase during humid periods, and essentially this could be due to several factors, including direct precipitation and algal scavenging, so the drawdown by biotic creatures and organisms, and enhanced organic matter burial in the sediments. There we go. This is a QR code for the presentation that I gave at INQA last year in Rome. The manuscript is currently in review for this paper, so hopefully it should be out for you fairly soon. But until then, if you are interested to see more of the figures, have another look and see and ponder over this some more. Like I said, there's a QR code there, so if you scan that, the slides that I presented at the conference will be there for you to look at your leisure. And finally, the final part of what I'm of this kind of story journey, if you like, is going back to Lake Ohrid. And I know we're not meant to have favourites, but this lake is my favourite, so I'm not ashamed of that at all. And this record in particular is absolutely fascinating. So this record goes back 1.3 million years. It's one of the longest terrestrial sedimentary records that we have currently for the Quaternary. And given the length of this record, we could ask a really unique and rare question. So how has the mercury cycle, or how has this lake retained mercury across multiple glacial and interglacial cycles? So the past sort of chapters that I was referring to, we were just looking at the last glacial cycle, so the most recent glaciation. With this record, we can look at multiple glacial cycles. And so look at whether mercury is systematically changing between them, if their signals are consistent, and whether, or if there are differences, what could be driving these differences, and how ultimately predictable is the mercury cycle between glacial and interglacial climate conditions. So to start off with, we found that the deposition of carbonates in this lake was affecting the mercury concentrations quite significantly. I won't go into too much detail with this because it could be its own talk in itself, but essentially what we had to do is first we had to correct for the carbonate. And so what that meant is we had to subtract the amount of, also at least calculate the amount of mercury that we would have in the lake if it wasn't being diluted by the deposition of this carbonate, which in Lake Ohrid is predominantly endogenic calcite. And so once we calculated this, we could then start to think really about what the mercury was doing throughout time. So this statement again, mercury supply appears to be one of the most important things as it relates to mercury signals in this lake. However, one thing that is important to note with this as well is that it doesn't seem to be doing, or at least in Lake Ohrid, there doesn't seem to be a very consistent signal of glacial and interglacial variability throughout. So we have, up to a certain point, we have, or rather, I'm getting ahead of myself. Actually, I've just realised I've got ahead of myself. So the point of this slide, and ultimately the main take-home message, is that when we're thinking about the host phases, it's only quartz or the detrital fraction that really correlates positively with mercury. when we think about organic carbon, that was actually a negative correlation. And so that's suggesting that, in fact, the higher the organic carbon is, the lower the mercury is, which, if you'll recall, is quite different to like the subtween, for example. But this relationship between mercury and the detrital phase, again, it's fairly weak. It's not a really conclusive relationship, and in particular following the carbonate correction. So if you didn't correct for the carbonate, you've got a really strong correlation between the amount of mercury in the sediments and the amount of quartz in sediments. However, when you correct for the carbonate, this relationship becomes a lot weaker, which suggests to us that actually it's not solely the availability of the detrital fraction that's driving drawdown of mercury into this lake. There are other things going on too. And I've included the results for Spearman rank rolling window analysis in this slide, just to illustrate the point that as well, it's not just about a weak correlation between mercury and the detrital fraction. Actually, this relationship is also changing a lot during time. It's not just a stationary relationship all the way through. And so already we can see this length of this record is affording some really interesting insights into how mercury is interacting with different sedimentary components, and ultimately that it is interacting in different ways over different time periods. And so if we know that mercury supply, so one of the mainly important features is controlled by the size and stability of different, what we call source reservoirs. So where mercury is being stored in the catchment, the size and stability of these will dictate how much mercury is actually getting into the lake, how readily mercury is removed from these reservoirs and transported into a lake, and how effective this transport is from the catchment to the lake itself. And so given these are the key factors driving change in mercury supply, what are the key factors about Lake Ohrid that would predispose this lake to having such pronounced, because you'll see in the blue box there, we typically considered over the length of the record. On average, we have higher mercury during glacials, so during glacial periods. Why could that be, and what could be driving an increase in mercury during glacials? Well, it's an open basin, which means that you've got inputs from rivers, precipitation, groundwater through a karst system. So you've got mercury that could be coming from lots of different angles. It's tectonically active, and so you've got ground movements, you've got differences in sedimentation as a result of these. High sensitivity to vegetation, and so you've got the vegetation that is essentially waxing and waning in relation to glacial climate variability, and so you've got really profound changes in the catchment, and that also relates to the changes in sedimentation, in particular high detrital matter fluxes, which is enhanced during glacials by the recession of vegetation, soil degradation, and the thinning of soils too. You've not got a very productive ecosystem when there's less rain, it's drier and it's colder. And so with all these things in mind, we can say, okay, these are some of the factors and special things about Lake Ohrid that could facilitate enhanced mercury supply during glacials as a general rule. But, and it's a big but, this isn't consistent throughout. This glacial rise in mercury is not consistent throughout the record. And so what you're seeing here is the result of a spectral analysis when we ran it on the mercury data. And as you can see, before 780,000 years ago, the dominant frequency, or at least the dominant cycle that we see in mercury with the increase decrease, is about 43 to 45,000 years, which is broadly equivalent to the obliquity orbital periodicity. And so that's suggesting to us that dominantly mercury is varying according to glacials. But after 780,000 years ago, there's a weak 97,000 year component, which suggesting that part of it may be related to orbital forcing still, because that's related to the eccentricity mode of climate change. But then you've also got, it's a lot less clear, and you've not got the dominant signals are most likely related to noise. So these large 564 and 270,000 year cycles appear to be more noisy. And so this increase in noise and reduction in cyclicity following 780,000 years ago essentially suggests to us that something has happened, something has changed in the system in that time. Of course, the mid-Pleistocene transition is one huge candidate for this change. And not only is the mid-Pleistocene transition documented in European proxy records, but it's also documented in Lake Ohrid too. So you've got changes in the pollen counts, changes in sedimentation, changes in the diatoms preserved in this lake. All these changes that are ultimately signaling major alterations in terrestrial biomass, continental ice accumulation, and sedimentation. And all of these we know to be critical to the terrestrial mercury cycle. And so all of them could have interlinked and sort of interacted with each other to elicit this increase in the irregularity or increase in heterogeneity that we see in the mercury after 780,000 years ago. And so there are two implications of this finding, or this shift in mercury cycling after the mid-Pleistocene transition, and these are not only could change in lake chemistry, depth, morphology, catchment structure, all dictate the extent to which global scale climate changes affect how mercury is cycled in these systems, but also that these major climate transitions, these major and abrupt and really distinct climate transitions, could have effects on mercury that cascade and that have feedback driven effects that propagate long after the transition has happened itself. You know, for example, we see the transition roundabout here in mercury, and you see all of a sudden a net increase here, and actually a shift in the baseline mercury to a higher level. And so this is suggesting to us that the effects of this transition they weren't short-lived, they lasted a long, long time. And so with that in mind, it's really important for us to consider how, or at least recognize that these kind of very abrupt climate transitions have the capacity to impact the mercury cycle in this way, and the effects, you know, aren't going to go away as fast as maybe the transition occurred. So they're not going to scale linearly in time as well. And so ultimately, what can we learn from these lakes? What lessons and key take-home messages? First of all, that mercury enrichments are produced by terrestrial lakes are produced by elevated mercury supply or inputs, rather than solely the availability of a host phase like organic carbon or the organic matter and the detrital fraction. Climate variability on local, regional, and global scales could all influence terrestrial mercury cycle and also be detected in sediments too. However, the lake itself and the characteristics of the lake itself constitute a really important control on these mercury signals too, and how the mercury cycles of these systems respond to climate, such that you're unlikely to find two lakes that have identical stratigraphic signals. You know, there are going to be factors related to each of them that influence the signals that they produce and how mercury is preserved in these records. And so, of course, lots of new questions to ask. And, you know, these are just some of the questions that I hope will be answered in the future. And they're questions that I'm taking away from my PhD, and hopefully with a chance to investigate further as we go forward into the future. But I think they're really exciting ones too. I think they're questions that are certainly answerable, and I think they will only become more clear with the increasing development of lake sediment records like this and long mercury records with the same kind of resolution, you know, where you can start to look at 100,000 year variability and the speed at which changes in mercury occur related to different sedimentary changes and different environmental changes too, you know, changes in the catchment, vegetation, all these kinds of things. And also looking at other major climate transitions of the Quaternary, so, you know, the strengthening of the Walker circulation in the tropics, the Quaternary glaciation as a whole, you know, could these major transitions have impacted the mercury cycle too? Or if not, what factors could be driving that, you know? So lots still left to do, but equally exciting. And so I want to conclude today by just acknowledging some of the members of the incredible team that I've had the real privilege of working with throughout this past 4 years and on this work. And, you know, it feels quite kind of an understatement to put them just on a slide to say thank you, but these people really have made a huge impact on me and my work, and I would not be doing what I'm doing now, going on to the postdoc, and I would not have the same love for science that I do now if it was not for the opportunity to work with these people and learn from them and interact with them. And so, yeah, they deserve a shout out here, and I think they're a fantastic team, and I'm very, very, very lucky. And so with that, thank you so much for coming to listen this afternoon. I hope you found it useful, and I will happily take any questions. I'd love to hear any of your thoughts or ideas or anything like that. So yeah, thank you so much for your attention.
Thank you so much for this great talk, Alice. It was really interesting. Just a quick reminder, if you have any questions for Alice, please send them to the questions that Paleoparks hosts, and then we will read them out loud. So in the meantime, we already have some questions, and as I said, I will post them in the chat as well as read them out. Just a reminder, you can send your questions anonymously or with your name attached, whatever you prefer.
Have a nice.
We already have one question. I will just leave that here from Thorsten Habetzettel. I hope I pronounced it correctly. Great talk. Have you ever thought about mapping mercury in surface sediments of one system, or compared two cores from one system?
That's a great question. It's actually something that is a project that's ongoing as we speak. In classic PhD fashion, I've got data sets that I haven't got in my thesis, but that are that still need analysing. And so we actually have a second core from Lake Ohrid. We have what it's called the Pestani core. It was taken in the same drilling campaign as the deep core that I was talking about just then. And it's taken slightly to the east. And even though it's taken nearer the shores, and so it's not got the same resolution, or at least the same continuous nature as the deep record. We're running mercury analyses on that too. We've got to about 600-700,000 years back now. And so with the main goal of, like you so rightly pointed out there, comparing the two and seeing whether, with the hypothesis of, given that they're literally in the same basin, we'd expect them to be very, very similar. And so if they're not, that'll give us something really interesting to have a look at. Although I can't give you any teasers on what we're going to find just yet, though, because I need to align the age model on them. And I mean, I've got lots of data that needs sorting out. So, but no, it's a work in progress, and it's certainly a really interesting question. And equally for other lakes too, Ohrid is a great example of a lake where you've got lots of cores available. But I think the more diverse environments that we can do these kinds of studies on, ultimately the better in the long term.
Thank you. I think that was a very clear answer. We have another question from Mike Sawaski. He's asking if the abundance of mercury is related to the source, and if volcanism is a source, and did you look at the volcanism records over this time?
Oh, such a good question. And actually one that's kind of ironic, because this project did not start off as exploring the Quaternary mercury cycle. It started off as sniffing out volcanic fingerprints using mercury in the Quaternary sediment records. However, we found in the first 6 months that actually you could not detect volcanic eruptions with mercury spikes in these sediments at all. And so my PhD went up in smoke. And so we had to make a small pivot. But really the underlying theory behind that was, if you look at the deep time sediments that I alluded to, you've got evidence that mercury enrichments are preserving episodes of large igneous province volcanism, so these million-year episodes of huge volcanic activity. And so the hypothesis was, well, could we detect single volcanic eruptions in higher resolution lake sediment records? And so we went in with the assumption that maybe we could see these mercury spikes corresponding to volcanic eruptions. And we explored this both in terms of ash layers. So Ohrid and Prestwood both have volcanic ash layers in them. And there was no mercury perturbations that were measurable prior to, intra, or after these ash layers, which was surprising. And equally, when you look at the volcanism over, you look at the net frequency of volcanic eruptions relative to the mercury perturbations, you just can't disentangle that from catchment-based processes. You couldn't say, so for example, in Lake Prespa, you have the big spike, the sort of bigger peaks in mercury in the Holocene. Was it there? Yeah. So you see an increase in mercury concentration here during the Holocene, and you also at the same time see an increase in the number of volcanic eruptions in our volcanic record. However, it's likely that this is not due to an increase in volcanism. It's actually probably to do with an increase just in the number of eruptions that are observed and known in the record, and so when you go further back in time with volcanic records, you have the issue of sparse recording, and so it looks like there are fewer volcanic records the further back you go, or eruptions, when actually there's just more eruptions that have been lost from the record that we don't know happened. And so trying to disentangle those is really, broader global trends is really difficult. And so if you don't have then mercury enrichments corresponding to the ash layers, that sort of adds a final sort of nail in the coffin to think, well, we're probably not going to see anything. And even if maybe there was a perturbation to the mercury cycle by a volcanic eruption, it's likely, because eruptions are typically less than a year in duration, it may be they perturb the mercury cycle for a very short period of time, shorter than the window of resolution that we can get in sediments of this age. You know, that even like Prespa with the resolution was about 50 years. That it may be that's just too large a window to capture any volcanic induced perturbations to the mercury cycle. So a lot of factors conspired against it, I think, but ultimately it looks like lake sediment records on these timescales don't appear to capture any enrichments for volcanism that can be disentangled and conclusively isolated away from catchment-based processes and other environmental phenomena.
Thanks a lot. Very clear explanation. Was actually wondering that myself as someone who mainly knows mercury as a lab volcanism indicator.
Okay.
So Torsten and Mike, I'd say thank you very much for the answer. We have another question from Katrik Sandosa-1. He asks, how important is the biological accumulation of heavy metals, so in this case mercury, in animals of higher trophic level, and by effect also populations of such animals in affecting the global mercury cycle?
This is a great question. There's only a limited amount that I can, I guess, speak to, because this is very much focused on the sort of contemporary mercury cycling. And I've got, there are people who are far more versed to speak on this than I am. But yeah, it's for sure important. And it kind of speaks to the point that I was referring to a bit ago, related to the different reservoirs and terrestrial environments in which mercury is stored. And so when we're thinking about how mercury is moved around the environment, you've got these different places where it can be stored and eventually mobilized and deposited and sequestered into geological materials, so sediments, rocks, that sort of thing. If you've got more, the problem in the modern day that we have is that, or rather, should I say, in geological time, when humans weren't mucking up the environment, pretty much, you had this natural balance of mercury being emitted from the solid earth by volcanoes, by geothermal activity, and these kinds of things. And it would be cycled through the atmosphere, through the terrestrial realm, and it would be a very balanced cycle. And the problem we have today is that we are emitting or bringing mercury from the solid earth into the atmosphere and environment at a much faster rate. And so the balance is completely off. And so it means that you've got this much higher susceptibility of bioaccumulation in terrestrial flora and fauna. And especially there's studies as well that come out that say that, higher temperatures and these kinds of climate changes actually favor processes like methylation of mercury. So that's where you have the conversion of mercury to these bioaccumulating toxic forms from interactions with different environmental materials, if you like. And so not only do we have more mercury actually around in the terrestrial environment, we also have more susceptibility to it being sort of methylated and bioaccumulating in the surface environment. And so to your question, yeah, I imagine that the organic plants and animals are constituting an even more important sink or reservoir for mercury in the modern day and age, to their detriment as well, because of course bioaccumulation of mercury is, as we tragically with the Minamata disaster, mercury poisoning is not nice at all. And this is a particular worry for the Arctic, where you've got, a lot that what we call things like the cold condensation effect, where you've got more mercury being transported to the poles and being deposited in these high latitude regions. And so there's a big concern about sort of Arctic fish and animals and people bearing the brunt of a lot of this mercury contamination. But I will also say that there's a sparsity of records actually and studies in the tropics looking at mercury cycling in the tropics and how rainfall, because as we saw with Assumptui, rainfall may actually be really, really important for bringing mercury into the surface environment too. And if you have more rainfall and more flooding in these kind of tropical regions, maybe that could have more an effect on mercury too. So it's my answer ultimately is probably, and I suspect it strongly, is a case that living beings are becoming more susceptible to bioaccumulation of mercury, but exactly how and the dynamics of that are still very much still a lot to learn in that respect.
Thank you. I think that was a very concise answer. I have another question that is somewhat related, I think. So the question is, do anthropogenic factors influence the mercury signal? And are there chances of the signal contamination due to temporary mercury accumulation in the sediments?
Yes, so ultimately, yes, human beings and anthropogenic activity is the most significant perturbator of the mercury cycle in the modern day and age. And actually, anthropogenic activity is the main reason why we're really struggling to study the mercury cycle without looking further back in time, and why looking further back in time is so important now, because because of anthropogenic activity, you've got, sediment records, oceans are just so swamped and contaminated with mercury that it's hard to actually disentangle and understand which signals are natural and which are anthropogenic. And it becomes a very muddy, very complex thing. And so that's why we're now seeking to look further back in time, where you've not got humans mucking everything up, essentially, and where you can start to isolate different factors. And then, because once you have that information, you can then think, well, relative to human activity, how important were natural processes, and look at the two compared to each other and think, well, how if you superimpose human activity on top of these environmental processes, what kind of effect could you expect? Would they cancel each other out? Would they amplify each other? Would they, one reduce the other? So that's a key question at the minute. But absolutely, mercury cycling is at the mercy of anthropogenic activity at the minute, and I don't think that's going to abate for anytime soon, because human beings don't seem to be slowing down with the industrial activity. And I should say as well that it's human activities. When I say that, it's mainly things like industrial pollution, so burning of fossil fuels, artisanal gold mining, so mining practices tend to be bad. Deforestation as well, by liberation of mercury from sort of vegetation sinks. They're kind of the key but the processes driving mercury cycle changes. But of course, there are lots of different factors too. So they're just the kind of main ones. When you think of dirty human activities and industrial pollution, it tends to be that kind of stuff.
Thank you again for that answer. Do you have time for a few more questions?
Of course, yeah.
Okay, great, because we still have a few. So Cassandra Suwan has another question, and he asked, although mercury radioisotopes are stable, how important is fractionation? And are certain radioisotopes more readily available for sequestration as compared to other mercury isotopes?
This is a fantastic question, and one I don't feel like I can answer, because we've been focusing mainly on just measurement of mercury concentrations and accumulation rates. Mercury isotopes is a field that I'm a lot less familiar in. Isotopes aren't something that we measured in this study in particular. What I do know is that mercury isotopes can be very good in terms of distinguishing different sources of mercury in the environment, and you can start to get a real handle on where the mercury is coming from in relation to the isotopes and how they change. And I know that the ice core community have really drawn upon this quite well in measurement of the mercury isotopes in ice, which can be quite, given how mercury is quite a complex element, it makes measuring it in ice by the means that we were doing, so by combustion methods. Whereas the instrument that we use essentially is like pyrolyzes the mercury, so you burn it at about 1,000 degrees and measure the mercury off it. Obviously, with ice you can't do that, and so I know that the ice core, like I said, the ice core community have been really drawing upon this mercury isotopes. And I think a paper came out in Nature last year that was looking at the last glacial maximum using mercury isotopes in ice cores from the Arctic, or I think it might be Greenland actually. So yeah, it's something on the rise, but I'm afraid I can't fully answer that question, perhaps to the detail that it deserves, just because isotopes weren't something that we were looking at specifically here. But if you'd like to drop me an email, we can certainly have a chat about it over that, because I can send you or at least direct you to the literature that is really good. There are some great reviews out there for mercury isotopes that are well worth a read if this is something that interests you. But yeah, I'm sorry I can't give more details on that.
Thank you. That's more than fair, I think. if you have some more time, we have another question from Sandro Saban. I think for this, it's better if you read the question and go back to the correct plot. So it's what exactly changed to the 800 kiloyears time period in the mercury QZ plot for 50 kiloyears. I think that caused the shift from consistent positive peaks to negative values.
So is it this one or is it this one?
Sandra, if you could quickly type in the chat.
Oh, okay. Yeah, I can see.
The previous slide, he says.
Yeah. This one. Yeah, great question. So this is an interesting one because, in short, we don't entirely know, because there are lots of interacting factors. This change in the relationship between mercury and the tritral fraction does correspond to that window in which the mid-Pleistocene transition was occurring, and so you've got essentially the intensification of the glacial and glacial cycles. I kind of skirted over it because I was aware that I was going a bit close to my time, but essentially during the mid-Pleistocene transition, you had this shift from the sort of 40,000 year periodicity of the glacial and glacial cycles, which I illustrated in this figure here. You had these more frequent glacial interglacial cycles here, and during the mid-Pleistocene transition, something changed. What exactly changed, we still don't know, and that's still a topic of immense fascination to the paleoclimate community, as I'm sure a lot of you will know. And we changed to these 100 kiloyear glacial cycles. So the glacial cycles not only became longer lasting, but that also meant they became more intense and had a much more profound effect on the environment. And so one possibility is that with this intensification of the glacial cycles, you also had intensification of processes that would drive increased mercury supply to this lake by and also corresponding to detrital minerals too. So increased erosion, decrease in the stability of the vegetation in the catchment, soil degradation. And so this is possible that this represents the intensification of those processes that were perhaps influential prior to the mid-Pleistocene transition, but also a lot more severe afterwards. One thing as well that I didn't mention in as much detail is the fact that Lake Ohrid has also been progressively getting wider and deeper throughout its history. And at this point here, at sort of roundabout, so between 600 and 800,000 years ago, the lake underwent a pretty major shift in, it became substantially deeper and wider, and it became more analogous to the basin that we see today. And so whether that widening and deepening has anything to do with it too, maybe a change in sedimentation, that's also a plausible mechanism. However, I say mechanism, the mechanism by which a basin widening or deepening could impact mercury cycling is a little bit ambiguous and a little bit nebulous. It's not 100% clear what would actually cause that, or whether the mercury, and what would drive a mercury cycle to shift simply due to a change in sedimentation related to a basin. And so there's lots of hypotheses that could explain this, but it's ultimately, I think the main take-home message that we at least focus on here is the mercury cycle was not the same after 780,000 years or so as it was before. And so you've got this change in this fundamental change that happened around about this between the 800 and 600,000 year period, and that lasted up until the present day. And so that's the main, I guess, take-home message of this plot for now. But we're trying to think of ways to continue exploring this idea and this the reasons for this change, essentially, and why it happened, because I think it's fascinating. I think it looks really intriguing, the fact that you have this really profound change. And so really disentangling and drilling down on the mechanisms by which this happened, I think will be a really cool thing to do in the future, and something I think that'll become a lot more will be facilitated by development of similarly long records. So can we get other lake sediment records crossing the mid-Pleistocene transition, where we measure the mercury and see if a similar shift occurs, because then we can start to think, could it be something to do with Lake Ohrid, or is it something that was happening on a global scale that affected all lakes, and the environmental changes that happen on a global scale, was it that instead? To what extent were these two things interacting, and how important were they equally? I hope that answers your question okay. And like I mentioned, more than happy to continue chatting about this over email, because I think it's fascinating and I could talk about this all day. So yeah, I hope that's all right.
Yeah, thank you. That was a great question. Also, Karthik says thank you for answering his questions. Yeah, I think since we are at the top of the hour, I would like to close the question session. Again, as Alice already said, you can contact her at a later point via email. So Alice, I want to thank you again. Massive thanks for your great talk and your great answers to the questions. So before everyone leaves, I would like to share my screen again for some final announcements, as usual. So once again, thank you for joining us. Once again, we would really appreciate it if you can fill out the weekly feedback form so we can keep learning. As promised previously, here are also Alice's socials in the chat and her email. So if you can reach out with questions, feel free to do so. And then I want to invite you all to next week's seminar on the 2nd of July, normal time, 15 UTC. This will be given by Jeanette Pierlo, who is going to talk about comfortiers from North Central Florida, so vertebrate paleontology from California State University in the US.